All right, hi everybody. Welcome to Chapter 11, Linear Optimization Models. This is going to be a direct follow-up to what we worked on in Chapter 10. We set up some of these models in a way that allowed us to do what-if analysis to help us to make decisions based on, well, what if this many people show up to the venue? What if this happens? What if this happens? And looking at possible profits we might see based on those numbers. But in this chapter, we're going to be looking at optimizing those decisions. Basically, if we set up a model like we did before, what would be the optimal number of people to show up given a series of constraints or restrictions? So optimization problems are used to support managerial decisions. These help us make better decisions through, advanced mathematics that take place on a simple spreadsheet like Excel. They are always going to be looking to maximize or minimize some function. Something is going to be a value, a numeric value is going to be maximized or minimized. And this function that we're maximizing or minimizing is called the objective function. It's going to be a term you're going to see a lot, objective function. That's the objective. What are we trying to do, right? That's the objective. There's a series of restrictions put upon us, and those are known as constraints. And then they can be linear or nonlinear. We're going to be looking at linear problems, nonlinear. Gets a little heavy. We're not going to get into that in these. In this class. So let's focus on the linearity, meaning going from point A to point B without any kind of outside realms that you could travel to. Linear, I think, a line, right? We're going from point A to point B on our optimization. So here's some typical types of problems you would solve this way. You need to make a production schedule and an inventory policy that's going to make sure that you have met all of your possible demand for however many periods in advance. But also you want to minimize the total production and your inventory cost. Okay, so what does that mean? I need to get I need to make 100 chairs, right? I'm a furniture place. I don't know, that's the first thing that came to my mind. I need to make 100 chairs. And I have so much wood available, so that's the inventory, and I need to keep the cost as low as possible, but I need to make at least 100 of them. So how can I make at least 100 of them to satisfy the demand? How do I schedule my employees, or what specific product do I make? Maybe I'm stocking the store and I've got 2 different versions of a chair, and so I can make some and they take this long, and I can sell them for this amount of money, or whatever the case is. Those are all the possible constraints that we can plug into this formula and then run it through the solver tool, and it will solve the problem for us. Here's some another typical one we might see, and I think you're going to see this type of one here, where there's an analyst looking to invest money into a portfolio and looking at maximizing the return on investment. So minimizing total cost, maximizing return on investment, maximizing profits. Just think, if it's a maximize or minimize problem, what are we trying to do? We're trying to make money, we're trying to save costs, we're trying to maximize returns, we're trying to minimize the time it takes to do something. Here's another one. You've got an advertising budget, and you're gonna advertise on various types of media. So the internet, radio, television, newspaper, magazines, they all have different amount of audience they reach. You're only allowed to run so many ads because maybe management's got a certain decision in their mind that they don't want to run more than 10 of any one particular type of ad. They want to diversify, or whatever the case is. Just because it's not a physical limitation, like, you could run more ads, but the restriction or that constraint could be a managerial decision that's over your head that makes this decision for you. We're only going to spend this amount of money. We have more money, but we're going to only dedicate this much of our budget to advertising. So that becomes a constraint, even though it's not binding in the way that we see it mathematically binding. It's part of the problem, because there is more money. More money does exist in the grand scheme of what the operations budget is. but decisions made by people above you can also be constraints. And then you've got a warehouse, and you want to determine how many of each, which warehouse should ship from one location to another. We saw that in our setup problem last chapter, where you did just an equal sum and a sum product to kind of see that. Well, in this chapter, those transportation type problems to determine how many are going to ship from one to another, we're going to actually solve. So linear programming is another name for linear optimization models. Have you ever heard of LPs or linear programming? That's what these are. Here's a simple setup for maximization problem. So this place makes golf equipment, and they decided they want to start selling golf bags as well. Okay. The name of the company is Par. Nice. And they're going to buy all of their distributors, Par's distributor, to buy all the produced bags at the end of the third month. So we have 3 months worth of making them all. We're going to manufacture them over the course of 3 months, and then the distributor is going to buy all of them, however many we can get made. So we have to assume some things going into this. How long do we have? How much time do we be able to cut and dye the material? How long to sew the material? How long to do the finishing of the material, which would be like inserting club separators, umbrella holder, how long to inspect and package it. And so you're given a series of requirements for each one of those bags, 7/10 of an hour, right? So you'd write that as 0.7 hours, half an hour, 1 hour, 1/10 of an hour. So that's how long it takes to do these. This is how long it takes to do the deluxe bags, okay? Now we're gonna get some more constraints. How many hours do we have available? Basically, how many employees that do this job do we have available that can do it for this amount of time? So this is how much we have available. So given these constraints, and knowing that the standard bags are going to make us $10 per unit in profit, versus deluxe bags only make us $9 a unit in profit contribution. So profit contribution, just as a quick refresher, is the so per unit, your sales amount minus your cost. That's how much it's contributing to overall profit. So it's the difference between your, it's just like saying profit per unit, right? That's the profit contribution of 1 unit, profit per unit. It's fine. So we would then develop some sort of model, and we worked on modeling last chapter. We're going to develop some sort of model where it goes from here to here to here to here, and we have calculation showing what the profit would be like if we did this. And then the solver tool will run, and it'll be, set this to the maximum, the highest volume it can do given the series of constraints. So when we set that up, we are going to do a couple things. One is we're going to formulate the problem. So formulating a problem is to write it out in words. We're verbalizing what's happening. So you verbalize your objective function first. So the objective is maximize the amount of profit given what our constraints are, right? Maximize profit subject to, and then you list your series of constraints next. So the second line is subject to these constraints, and then basically you're just writing out, you're saying out loud what the setup is, right? It helps you to kind of work through and understand, am I setting this up right? Does all of this make sense? It's kind of like talking to yourself, which I do a lot when I'm making these lectures. So it helps you to understand the problem thoroughly. It helps you describe the objective, describe each of the constraints, describe the decision variables, write the objective in terms of the decision variables, and write the constraints in terms of the decision variables. Okay, so decision variables are anything we can decide on, meaning how many of these products am I going to make? How much time am I going to spend on this? But not how much time is available, not how much of the resources are available. Those aren't decisions. Those are known quantities. Deciding would be how many of this do I make? How many of this do I make, right? Given they're going to use up all of this material, but only what you can actually affect are decision variables. So you're going to see the term decision variables quite a bit. typically there's only, like in a problem like this, what are we deciding on? We're deciding how many standard bags to make, and we're deciding how many deluxe bags to make. So there's only two decision variables in this problem. Back that up. So there's only two decision variables. So our objective is going to be, so in terms of the decision variables, our objective is going to be maximize total profit given $10 for every regular bag, $9 for every deluxe bag. And the constraints are going to be written in terms of decision variables. How much sewing time, how much dyeing time, etc. does it take for every one of the standard bags or deluxe bags do I make? All right, so describe each constraint. So constraint number one is the number of cutting and dyeing hours used must be less than or equal to the number of hours of cutting time available. Long sentence, but that should make sense. Let me restate it. So however much I use, I can't use any more than the time I have available. I think it said 630 hours, if I recall. I could back up. 630 hours of cutting and dyeing time available. So, but if I only have 630, I can't use more than 630. That's all that's saying. And so we can write this out as, in a formula, which you're going to see it written down in the formula. But as a sentence, the number of hours of cutting and dyeing time that we use must be less than or equal to the number of hours available. And that's true for all four of these constraints. The number of hours we use has to be less than the hours available. Pretty simple concept when you think about it that way. So then defining the decision variables, S, number of standard bags, D, number of deluxe bags. Now, why is it S and D? Well, because in this specific problem, we've got standard and deluxe bags. A variable can be any letter. It can be whatever. Sorry, my space heater came on. It's cold in the office. All right. So the variables can be any letter you want. So if you can choose any letter, then make it easy on yourself, as easy as you can, by picking a letter that makes sense to the problem, because it'll help you keep track of it as you're following it through each of these steps. Every time you see S, you'll know standard bags. Every time you see D, deluxe bags. Now, in the books that are on this subject, often they'll just choose like X and Y when there's two of them, or A, B, C when there's three, A, B, C, D when there's four. Just as a standard, or even X1, X2, X3, X4, and just always use that X and then the number, a subscripted number for each. And that's fine too. You can literally choose whatever you want, but you shouldn't. You should pick a letter that makes sense, that helps you keep track of it. It just, make it easier for everyone, the audience and yourself. And then writing the objective in terms of those decision variables. So if PAR, the company, makes $10 for every standard and $9 for every deluxe bag, then the total profit contribution is going to equal 10 times S plus 9 times D. So this is that written down as a formula: $10 for every standard, $9 for every deluxe. So that's the objective function. The objective function is maximize total profit contribution right here. Maximize total profit contribution, which is equal to 10S plus 9D. The most I can possibly make is $10 for every standard bag that I make, plus $9 for every deluxe bag I can make. So maximize profit equal to 10S 9D. Or this is even simpler than I've seen on other types of books like this. So then we write them out in terms of the decision variable. So this might look a little complicated, but I'm just going to go over it briefly on this, and then we're going to go over it more in depth in the practice problems video. But it takes 7/10 of an hour for every S. Now we're not going to write it as a fraction. I have genuinely no idea why it's currently written as a fraction, because they're going to adjust this to decimal points later. My assumption is that in later editions of this textbook, they've corrected this, because frankly, writing this out as a fraction is nonsense. But this is 7/10, so 0.7 for every S, plus 1 hour for every D. So 7/10 times however many S's we make, plus 1 for every how many D we make, deluxe bags, standard bags. less than or equal to 630 because we only have 630 hours available. And you might have stopped to think for a second and ask yourself, well, how many standard bags am I making? How many deluxe bags am I making? We don't know. That's going to be solved later on. That's what Solver is going to do for us. So we're going to set up this entire problem in Excel in a way that we're literally just clicking on an empty cell or a cell that you put a placeholder number. Because I usually put the number 1 instead of a blank cell, but I'm having one cell in Excel that says 0.7 and one that says 1, and I'm doing 0.7 times 1 or 0 or whatever number I've put in this placeholder box. And I've done this for every one of the constraints. I've referenced this potentially empty cell, and then the solver tool will actually change that cell to the number that fits all of the constraints and still arrives at the most possible profit we can make. So we're writing all these constraints out, there's 4 of them. And there's actually 5. So when we formulate the problem, there's always one constraint that you have to write out just as a test of academic knowledge, basically. The idea that you can't produce a negative amount of something. You can't say, well, if I make more on standard bags, let me free up a bunch more cutting time by making negative 1 billion deluxe bags. And now all of a sudden I have all this more time available. That doesn't work like that. You can't make less than 0. You can choose to not make any, but you can't make negative 5. That doesn't work. So we are just we have to acknowledge the fact that this is a constraint. This is a constraint that says we can't make less than 0. Fortunately, when you're running it in Excel, there's just a button you can check. So in the solver tool, there's just a button that says like make all values non-negative or something to that effect. You just have to check that. It's checked by default. You'd have to uncheck it to mess this up. It's just on by default because it knows you're not going to go negative with these constraints. When you're formulating it and you're writing it out as a word problem, you have to write this out to acknowledge the existence of it, right? If you don't write that out, you've missed out on one of the known constraints. Okay. So then you've got your 4 constraints. So you've got cutting and dyeing time, sewing time, finishing time, inspection and packaging time. You have your objective function here, maximize your profit subject to 10S plus 9D or equal to 10S plus 9D, meaning $10 for every standard, $9 for every deluxe bag, subject to these constraints. And then if we were to set this up properly in Excel with the proper amount of numbers in the right places and set it up just perfectly, we run this up, and it will plug in the exact amount we should make for S, the exact amount we should make for D, and it's solved. But that's the idea of a maximization problem. So we're just going to show just a quick idea of I think a minimization problem next. Okay, so before we go into the minimization problem, let's talk about let's talk about optimal solution. So for it to find an optimal solution, the optimal solution will have the highest possible value given all the constraints, but the optimal solution must also be a feasible solution, meaning that it exists within this feasible region of all possible answers. There are only so many amounts that you can actually make of S and D combined because you run out of resources at some point. So you could make nothing but the standard bags, you could make nothing but deluxe bags. You could make none of any of them, right? You could make 0 of each, in which case you've made no profit. It's still an amount you could choose though, right? That's still feasible. You could choose to not make any and make no profit. You wouldn't choose that. It's not going to be the optimal solution. And it's not usually to make all of one or all of the other. It's usually some combination of both. But the optimal solution will always lie within these boundaries. And these boundaries can actually be calculated on a XY scatter plot. within that feasible region, there's going to be what they call corner points, which are the extreme. There's 4 extremities. So if you think about like an XY chart, right? So let me see if I can write on the screen real quick. So if you think about like an XY coordinates, right? You've got the Y axis here and X axis here. Well, this spot right here is your 0, 0. And then at some point up here is going to be using doing nothing but deluxe bags, and then some point here is going to be how much money you make if you do nothing but standard bags, and then some point here is going to be the profit if you do some combination of both, right? So it's called corner point solution because you've got 1, 2, 3, 4 corners, and one of those corners is the optimal solution. It's always going to be the extremities of this 4-pointed object, which is just a cool thing that works out whenever you if you were to graph it. So with only now it only happens when there's 2 decisions. If you have more than 2 decisions, you can't graph it on an XY chart. But just to visualize that, here we go. I drew out that nice, amazing drawing. It's actually on the slide right here. So these are the feasible possible regions, and within these feasible regions are potential values we could make, right? So the answer is going to lie somewhere in here. We can't make this many of deluxe bags. We can't make this many up here because we've well run out of the amount of cutting and dyeing time, finishing time, etc. Right? The amount of time we have is only available in these answers here. Okay, yeah. So find the problem, it's going to be one of the extreme points. So basically, we take the XY coordinates, and then if we didn't have Excel, we could just plug in all of the coordinates of those points back into our original problem, which was 10S plus 9D, substitute the corner points for S and D, and just do the quick algebra and see which one of those results in the highest number. And those points become the amount we should make. We're going to mostly focus, though, on solving it in Excel. So with Excel, we're going to set it up in a certain way. It does, yeah, so they have you do that here. You just standardize it. Again, I don't know why they have it in the book as 7/10, 5/10. Just a ridiculous thing they've done here. But it should, set up as a decimal place. And then 5/6 of an hour should be set in this manner, etc. But you'll set it up in a certain way. You've got your constraints here. You then would have a spot here that shows how many you're making. And what they've done, they do what I do, which is they just plug in the number 1 here and here just to kind of see if the formula is working. And then from there, we if it's set up properly, you can run the solver tool and it should find an optimal solution. But we'll again focus on that more in the Excel video. So it found a solution, which is to make 540 of the standard bags, 252 of the deluxe bags. That's the profit. It uses up all the cutting and dyeing time, uses up all the finishing time, and then there's some other things that are left over. So this is what the answer report is going to look like in Excel. So there's some terms I need you to know because they're going to come up on your quiz. So before you've done your problem set, even if you've done the quiz first, some terms you need to know, and they are binding constraints, slack value, and slack variables. So this is just a report that prints in Excel. It's an optional report. You can check a button when you run the solver tool, and it'll print this off for you. And what this means is if you use all of the time available, you can see it says here that we used all the cutting and dyeing time, all the finishing time. Well, when we look at this report, we used all the cutting and dyeing time, which means we have none available to change, but we still have some sewing time and some inspection time left over. So there is a the amount we could use. If we had more of the other ones, then we might make a different amount. So we don't need more sewing time. We don't need more inspection time. Neither of those is binding us to this answer. The fact that I only have 630 hours of cutting and dyeing time, the fact that I only have 7 or 8 hours of finish time, I use all of that time up. And so those values are binding to give this answer here. They can't change. If these amount we had changed anyway, we would get a different answer here probably. Versus the non-binding time, I could have less sewing time available. It would not change the value in any way. So slack value, so that's slack value is the difference between how much we used and how much we have available. So that was that 120 versus the 0. So 120 here, 18 here. Slack value is how much in excess we have. You can see anytime you have 0 slack, you'll also have a binding constraint. They end up matching up in that way. By adding a non-negative slack variable, we can make the constraint equality. So we can add more available of these ones that are binding or non-binding. We can add more to that and still have you end up with an inequality, right? You have 480 is less than 600 on this formula because you didn't use all of it. But if you used up more of it, you could make this an equality instead of an inequality at the final one, because it's going to be less than or equal to. And typically it works out that you use all of some of them. So those are equalities. Okay, on to a minimization problem. I'm just going to kind of gloss over this one because we're going to work through this one in the practice problem video. Just the idea is that you're not always maximizing something. Sometimes you're minimizing something. In this case, they want to minimize the amount of total costs. That's a usual setup. Minimize the total cost. And they have to provide a certain amount of products in A and B to a customer. How many gallons of A, how many gallons of B? Those are decisions, but we have to give them at least so many gallons of A, so many gallons of B, or something to that effect. So we'll work on that, but this is how the setup ends up looking when you formulate it. You've written it all out. You've written out these constraints. You've got demand, production time, processing time, and the fact that neither one of them can be less than 0, so they have to be greater than or equal to 0. Set it up, and when running it in Excel, you'll see that you have the option in Solver. Like when we did Solver before, we were setting it to a specific value. Actually, we were going into the Solver tool in the data analysis tool back, but we're going into this Solver on What If, I think. But on the Solver tool, you have the option. Do you want to maximize it? Do you want to minimize it? Or do you want to set it to a specific value? Setting to a specific value is how you find like break-even point. We're focusing on these first two, maximize and minimize. And then this is that check mark I set, make unconstrained variables non-negative. And then the solving method, simplex LP, means it's a linear programming problem. This is not the default. I think it's alphabetical order. So you will always want to change this to simplex LP. So don't uncheck this box. You'll get a crazy answer. Do change it to simplex LP, and then make sure you're on maximize or minimize. Just give you a quick preview of that. So let's see. We've got some special cases. So sometimes the optimal solution can be at the at 2 different areas. So they found in this same problem, I said there was a corner point, but if you remember the map, there wasn't a corner. When they overlaid it, usually like in my drawing, there was 1, 2, 3, 4. But in this drawing, you can see there are 5 corners, and that's not usual. I glossed over that because it's not a usual thing. But this is one that happens to have 2 optimal points. It just so happens that there's 2 combinations we could do, that both come up with the exact same amount of profit. And we're using very simple numbers, so I guess I can explain it, but both of these end up with a different amount. If the, okay, so not at 10 and 9, but only if they had $6.30 and then $9 were the amounts, then you can create two different points. So they found a certain combination of dollars where both times the profit ends up coming out to $5,670 is the optimal solution for it. Or, yeah, 5,670. Infeasible. So sometimes you'll see that there's just not a feasible solution. Usually that's because you've set an unrealistic expectation. You've said we need to make this much profit, or we need to do all of this without enough resources to do it. Then it's not feasible. You plug it in and you can show, hey boss, this is not doable. You know, I said originally it wasn't doable. It turns out now I can mathematically prove it's not doable. Or you've just made too many restrictions altogether. So expectations too high, too many restrictions. The other time you might not find a feasible solution is because you've done it wrong. Don't discount that. If you're doing any of these problems in the book and you don't find a feasible solution, something's messed up. Because all of these problems in the book have a feasible solution. I'm not going to give you one that doesn't have one. And okay, so let's move on. We've got resources being used. Infeasible solution when you use a solver. Yeah. So typically it's going to pop up and say it was not able to find a feasible solution. You just have to go through it step by step to figure out where it is. You can, if it was something you were doing in real life, you could remove one of the constraints altogether and then try to resolve it and see if that does it, in which case there's just a problem with having that constraint altogether. In this class, if it doesn't find it, something's not formulated right, which, you know, if you've never done LPs before, it takes a little while to wrap your head around. Once you get it down, I think they're fun, but you know, until you get that down, you're gonna make mistakes on this, and it's gonna take some trial and error to figure it out. And don't freak out because that's just normal. You know, keep at it. All right, so unbounded problems. We're not going to really work on unbounded problems, but let's look at sensitivity analysis. The sensitivity analysis is asking us how much would I need to change the objective function to affect an optimal solution? How much could I change, and how much would more of a certain resource affect the optimal solution? If I had more of this, would this number change anyway? And we can look at that, the shadow price, which is also on that printout. And the shadow price for constraint tells us how much the optimal solution changes for every single one unit on the available resources. We increase our time. So here's an example of that. So we have a problem where number of gallons of A and B, the minimization problem. We had 350 and 600 available to us of these things on the right-hand side of this formula. Well, in this printout, the sensitivity report, slightly different report than the other one. The sensitivity report will tell us the shadow price. So for every available increase, so if I had more production time available, the value for everyone, it would go up by $4. Now, this was a minimization problem. We didn't want it to go up. We actually wanted to go down. But if I had more processing time available, then our cost could actually be lowered by -1. And so in the constraint, this is the current value. This is how much you could increase that by, and this shadow price is true. So I could go up to 100 more, and this -1 is true. I could decrease it by up to 125, and this amount would still be true. I could increase it by 125 here on the right-hand side. And the right-hand side is the amount of the resource I have available. I could increase it by 125, and for every increase, I make $4. And then the decrease would be true as well. I could decrease it by 50 and save, it would go the opposite way. Now, if you see this 1E plus 30, that for some reason, I don't know, I've always been meaning to look it up, but this just means error, or it can't be done, right? It's an error. Think of it as an error. Just look at the E and think error. You can't decrease the amount. You cannot change this by 0 and decrease the amount. You can increase it by 125 and nothing would change, but you can't decrease it because it would break the formula in some way. So that's how you read a shadow price. If you had more of this right-hand side available, it would change the total objective function, which came out to whatever it came out to. I didn't even know the answer because we skipped over it. But whatever the answer was, it would change by this amount. That's true up to this much more. That's true up to this much less. And you can see under the variable cells for the amount they produced, 250, 100, you could increase the amount you made. You could decrease the amount of this one you made, but you couldn't do the opposite of either one of them. All right, what else we need to do on this one? We've got, yeah, this is just a general example. So often you'll see that they subscript X1. So standard bags, instead of S and D, they did X with a subscripted 1. If you have a lot of decision variables, you can just write them out in order and then keep track of them that way. What's also nice about that, if you had a series of problems and you had to do everything from scratch, you could just use X1, X2, X3, X4 for all of them, and then just copy and paste most of your work. Let's not undersell the importance of being able to shortcut. So that is an advantage. The disadvantage is you can't as easily identify what that model, what that represents in the model. So on these simpler ones, using S and D, they make sense. Now, if it was some other value, maybe it was you have 4 variables and 2 of them start with the same letter. Now you get into some dicey territory right there, right? General notation. So using this same structure where you've got all of the calculations on the left-hand side, all of the known amounts on the right-hand side. Sometimes you will have to have a formula on the right-hand side. You're going to see one of those in your problem set. I think I might have one for the practice problems as well. But sometimes, like, the amount that you invest into one has to be equal to the amount you invest in 2 other ones. So you're going to have a left-hand side and a right-hand side that both have formulas when that happens. Okay. Portfolio selection problems are always about returning the maximizing the expected return or minimizing risk. It could be set up that way. There's usually restrictions on what's allowed. There's laws preventing you from investing too much in one, not enough in another, company policies. So I will have this practice problem for you when we do the other video. Yeah, so you're gonna see stuff like neither oil nor steel should get more than 50,000 of the investment. All the government bonds get at least 25%. All of the high return get not more than 60%. So in this case, because you've got dollars invested in Atlantic, Pacific, Midwest, Huber, and government bonds, you could just do A, P, and HG. That's fine when you set it up. I don't know if it's preferable. When I'm doing a lot of them in a row, like I said, I'm going to want to copy and paste most of my constraints. If I write this kind of problem out once, I want to write it again and change this value on the right, and I want to change this value on the right and change this value on the left and keep all my X1s and not have to rewrite them. So it just kind of depends. If you're working on just 2 constraints total, just use simple letters. You're working on 4 or 5 and you're doing several problems in a row that have 4 or 5. Maybe this X with a subscripted 1 is the better way to go. And you can see on the practice problem, each of these Fortunately, these ones all have a solid amount on the right side, but on this one, X5, whatever that one was, government bonds, is to be greater than or equal to 25% of these other two combined. And this one has to be less than or equal to 60% of these other two combined. So you'll see where when you're formulating it, you have a reference on one side, a reference on the other. You don't have a given solid number like you do here. 100,000 total available, no more than 50,000, 50,000. Those are known numbers. You're just going to type those in. But here you're going to have some sort of references when you set these up. I guess let's touch on transportation problems. They're all about sending items from several locations to several demand locations. These might be distribution centers, they might be retail outlet stores, they might be directly to the customer. Typically, you're going to have a certain amount at one place. You know the demand at all their locations, and they're almost always set up in a way that minimizes the shipping costs, because it costs more to ship from, you know, Washington State to New York than it does to ship from Kansas City to New York. But maybe you have more available in Washington State, so you have to ship some from there, but you want to ship more from Kansas City. But then you also have to get some down to Miami, et cetera, et cetera. So these have to be set up in a certain way that requires just, you know, it's gonna look crazy, but just the idea that each one of these can ship to all four of the demand centers. Each one of these can ship to all four of the demand centers. So you just have to end up writing out a lot more constraints, every one of those possible combinations. So like, you know, demand center one to, or plant to distribution center. So from 1 to 1, it's going to be $3 for every one. From 1 to 2, it's going to be $2 for every one you ship, and so on and so on. And probably best to just leave most of this for the problem video, but you're going to end up with something that looks like this instead of a very simple constraint to the left side. This is why I started liking, you know, the X with the subscripted a little bit more when you get a lot of them, because I can copy a lot of this down and just change the number in the subscripting. So I write it once, and then I change Cleveland to Bedford, and I change 5,000 to 6,000, but then I change all the first 1s to 2s. I change all the first 2s to 3s. Saves you a little bit of time if you can do it that way. And then this just looks like crazy nonsense, but this will all be in a Excel spreadsheet. I have no idea why they made it look like it's you know, number letter explosion. This is in a very safe, contained spreadsheet. And this should look familiar. This is very similar to problem 9 from the last one, where we had items shipped from one place to another. It was solved for us. We had these amounts, but we would be, they give you a preview of what this, how this problem I think was actually solved, which is the amount that was shipped from one place to another. So solver will give us these values if we run it right. And then we can have a total cost in the middle of that. Okay, one last one was advertising campaign. The idea that we could have a budget, we need to have a certain amount of commercials run, and that we have to spend some money on certain advertisements. There's decisions made upon us, and that they're going to reach a certain amount of audience. The idea is to maximize audience exposure. So I think there's nothing new there other than just it's a different setup for a problem. So since there's nothing new there, I think let's just save that for the practice problem video as well. I just really wanted to make sure the terminology was here on this video, and just the general ideas of how these will work, help to try to ease your mind as we go into that. Just you know, stick with it. You got 2 weeks to get it done, and it's not as complicated as it initially feels, because these are all new concepts using a solver tool, etc. Just, you're going to want to watch the practice problem video, ideally on one screen while you work on the other. If you're someone who has struggled in the past, later on the week getting started on these problem sets, this one, start early, because if you have questions, I want to answer them for you. If you haven't been working with a partner on your problem sets, find a partner and work on them with them. Turn them in as a pair. It's faster grading because I have one paper to grade for 2 people. Everyone wins. So this might be a good one to do it. It's our last problem set, finish strong. And yeah, I think we've got nothing else terminology wise. So I will see you in the problem set video. You guys can do it. Thanks for sticking with it all semester long. We're almost at the end. Keep it up. Thanks, everybody.